Conics section 2 here is on the circle and the ellipse. So given the equation of a circle, we're going to complete the square if necessary to find the center and the radius, then graph the circle. Similarly, given the equation for an ellipse, we're going to complete the square if necessary, then find the center, vertices, and foci, and then graph the ellipse. First topic is on circles. The standard equation for a circle that has a center located at the ordered pair HK and radius r is going to be given by the equation x minus h squared plus y minus k squared equals r squared. In the first example down here, we have a circle that's not in standard form. It's been expanded. And so we're going to need to complete the square on this circle in order to get it in the correct form. Notice that in this form, the r value is alone on the right-hand side. So we're going to start by taking our constant, the 32, and moving it over to the other side. We're also going to group our x's together and group our y's together. So I'm going to have x squared minus 16x. I'm going to leave a space right here. Plus y squared plus 14y. I'm going to leave another space right here to complete that square. And then equals negative 32. All right, so for the x variable, when we complete the square on this one, we're going to have our 2n being negative 16. So our n value is negative 8. And our n squared value is 64. So I'm going to be adding 64 to both sides of the equation to complete the square on the x variable. On the y variable, since I've already used the letter n there, I'll use m. So 2 times m is going to be equal to 14, which would make the m value 7 and the m squared value 49. So I'll be adding 49 to both sides of the equation to complete the square for y. These should each factor. The x portion of this is going to factor with the x plus n, which in this case is going to be x minus, oops, that's supposed to be an 8. I was thinking 64 in my head, so x minus 8 there squared, because negative 8 plus negative 8 is negative 16, and negative 8 times negative 8 is positive 64. Then for the next portion with our y variable here, we're going to use that m value. So this should turn into y plus 7 quantity squared. Once again, 7 plus 7 is 14, and 7 times 7 is 49. On the other side of the equation, we just have a couple constants that we need to add up. Let me clear this graph right here. We need to take our negative 32 plus our 64 plus our 49, and this value over here is 81. I'm just going to rewrite that since it was a little messy. X minus 8 squared plus y plus 7 squared equals 81. So this is the equation for this circle, and I can find its center. The x coordinate is going to be positive 8, x minus an 8. With y plus 7, it's going to be a negative 7, or y minus negative 7. So opposites on both of those. And the radius on this one, since the r squared value is 81, r must be 9. Let's go to the next page. We get to talk about ellipses here on the next page. The definition first of an ellipse is the set of all points in the plane, the sum of whose distances between two fixed points of the foci, these are my foci here, is constant. So if you have any point and you add the distances between the two foci, that is constant. The sum is constant. That's just how they are defined. So you can imagine a string with 2 push pins and a pen looped around into it. You'd be able to use that string and those fixed points right here to trace an ellipse. That's the geometric definition. The center of our ellipse is the midpoint between the segment that contains those foci there. So that's where our center is. And then our ellipse also has some vertices. And in this situation, I want to point out before we get too far right here that we are going to start by looking at ellipses that are centered at the origin. So the center here is at the origin. My ellipse can be longer or it can be taller. So this is one first where the major axis, the longer axis, is horizontal. And in this situation, the equation is x squared over a squared plus y squared over b squared equals 1, where the a value is the larger value. So you have the larger value underneath x if you're going to have a major axis that's horizontal. Versus if you have a major axis that's vertical, now the larger value, the a number, is just underneath y instead. So that's the difference between, in the equation at least, if I can tell if it's going to be longer or taller. It's if the larger denominator value is under the x value or under the y value. All right. Continuing, we have our vertices, and our vertices are going to be a distance of a away on the major axis. So if the major axis is horizontal, it's going to be plus and minus a along the x-axis. Or if it's vertical, instead, it's going to be plus and minus a along the y-axis. Then the other 2 points, which are not called vertices, they're y-intercepts. In this case, they may have other names later or no names, or just the distance across the minor axis. Those are going to use the b number. So the smaller number is going to control the other direction. This smaller number controls the b direction. This smaller number controls the x direction. Underneath the y controls y. Underneath the x controls x direction. And you can see our other points here of interest in terms of being able to draw this ellipse. If I can identify where the center is, I can identify where the foci and these minor points are, I could connect my ellipse shape around those 4 points. The last point of interest, or the last item right here, is the foci. We mentioned those foci as important pieces in terms of the original geometric definition, and they are a distance c away from the center, where c is defined as a squared minus b squared. C squared is a squared minus b squared. They always go along the major axis, so you're using the same definition for c down here, but if your major axis is vertical, you're going to add and subtract your c to your y coordinate instead. Okay, so let's take an example here, look at this situation where my goal is to write the equation of an ellipse, and I know the vertices and the foci. Okay. So if I know my vertices, and they are at negative 5, 0, and 5, 0, and I know my foci, and they're at negative 3, 0, and 3, 0, I need to sketch my graph of my ellipse. I'm going to need to write the equation and sketch the graph. I'm going to start the graph. Negative 5, 0, so 1, 2, 3, 4, 5, and positive. All right, so those are my vertices, and then my foci are somewhere inside here at negative 3 and 3. What I don't know yet is how far up and down this is, but I do know that the major axis is going to be horizontal because I only call them vertices on the major axis. Okay, in the equation, I could actually kind of set up what the beginning looks like. I know x over a. I can find the a value. So the a value is 5, since I count out 5 in both directions right here. And I know the c value is 3. I don't need c for the equation, but I can use this statement about foci here with the a value and the c value in order to find b, and I do need b for my equation. So we'll have 3 squared equals 5 squared minus b squared. So add the b squared to the other side. That's going to be equal to 25 minus 9. So b squared is going to equal 16. And b would be 4 plus and minus, or you're going to add 4 and subtract 4. B is 4, right? So the b itself is 4. So we'll be counting up 4, it's a distance measurement, and down 4. Okay, so I can draw it based on knowing where these vertices are and knowing these, oops, I missed my distance right there. Okay, art skills not my forte. We can draw our ellipse type shape going through the vertices and through these distances across that minor axis. And I can write my equation now as x squared over a squared, so 25, 5 squared, plus y squared over b squared, so 16, equals 1. And if you take a second to graph this in Desmos, you'll be able to confirm that this graph here does match this equation. I'll go ahead and graph mine here. I have x squared over 25 plus y squared over 16 equals 1. And if I graph some of my ordered pairs, I have 5, 0, and negative 5, 0 as the two vertices here, and the foci are inside at negative 3, 0, and 3, 0. And then I have the nameless points that are on the minor axis, and those are at 0, 4, and 0, negative 4. And that is, again, what I attempted to draw on my paper here. The one on Desmos is a lot prettier. They were able to connect more smoothly between those points. All right, so let's take a look at this one right here. Here, the equation is already written for me, and I need to find the vertices and the foci and draw it. It is not in the form that we saw on the previous page. Namely, in the form that we saw on the previous page, we needed to have this equal to 1. So I'm going to divide both sides by 36 here and make sure to distribute this. So in the x squared fraction, when I have the 9 over 36, that's going to reduce to a denominator 1 over 4 here. And then for the y squared, this is going to reduce, and the denominator here is going to be 9, right? 4 reduces into 36 9 times, equals 1. Okay, so I can tell that this parabola is going to have a longer vertical axis because the denominator that is higher is underneath 9. So I'm going to start to draw it, and then I'm going to write down all the things I need right here. So it's going to go a distance of 3 up and 3 down, 3 being the square root of 9, and it's going to go a distance of 2 over square root of 4. All right, so this is what it should look like right here. And again, the vertices, almost said vertexes, which is not how you say the plural of that. The vertices are starting at the center and going up by 3. So they're going to be at 0, 3, and down by 3, so 0, negative 3. And then these points don't really have names. They're kind of important in terms of drawing the graph, but they don't need to be listed right now. They're just the lengths of the minor axis. So they're not going to go on my list here. I need to list the vertices and the foci. These are just my minor points. In order to find the foci, though, I need to find the c value. So c squared is equal to a squared, which is 9, minus b squared, which is 4. So c squared is 5, For C, we're going to have plus or minus the square root of 5. So we're going to go in the vertical direction, a distance of the square root of 5. So our foci are going to be at 0, square root of 5, and at 0, negative square root of 5. And those are the things that we have been asked to list, as well as draw. Okay, so I could draw my foci. I don't know how big the square root of 5 is, but it's somewhere in there. All right. Now, these last two examples were both for ellipses that were centered at the origin. Now we're going to think about ellipses that are centered somewhere else. So where the center of the ellipse is going to be the point H, comma, K. We can think about this as the same equation, but just shifted horizontally H units and vertically K units. And so you'll see your equations like this. All right, they're going to have the H shift in the X direction, the K shift in the Y direction. We still have divided by A squared divided by B squared, and still the difference between major axis horizontal is just which one has the larger denominator versus major axis vertical is just if the Y variable has the larger denominator. For how to find the vertices, well, we are still going to use the A number to count along the major axis, so along the x-axis, but we're now counting it from H. So we're going to have H plus A and H minus A for our x-coordinate. The y-coordinate stays at K. Same thing for the foci. We're going to take that H and we're going to count by C, up and down along the x-axis, so the x-coordinate there, leaving the k-coordinate the same. This length of the minor axis bit right here is 2b. I think it's easier just to think about it as b halfway up instead of having to think 2b across the entire thing. So it is 2b across the entire thing, but you're going to be counting up b and down b from those positions. So if you wanted to find those minor points, they need a better name, but they don't have one. You'd be leaving H alone and then counting K plus B and K minus B. Similarly, if your major axis is vertical, we're just going to add your A's to the K values instead, or vice versa for the minor axis, you'll do your B to your H values instead. Foci, again, on the minor axis is to the Y coordinate if you are vertical. All right, so we have ourselves an ellipse at the top of this page. Find the center of vertices and the foci, draw the graph. Looks like we're going to need to complete the square here also. So we're going to do some regrouping. So we've got 4x squared plus 24x, leave a space, y squared minus 2y, leave a space, and I'm going to subtract that 21 over to the other side. So we need to complete our square. First of all, though, I can't complete a square on any variable with a coefficient, so I'll need to factor that out. So let's do that before we do anything else. 4 times the quantity x squared plus 6x. Leaving that gap inside the parentheses here, we're going to finish writing down the rest of our equation. No factoring was needed on the y variable this time, so the rest of it is going to stay the same. All right, we're going to complete the square on the x variable first inside these parentheses. So 2n is 6, and n would be then 3, and n squared is 9. So I need to add a 9 inside of this parenthesis to complete this square. When I add the 9 inside of this parenthesis, what I'm really adding to this side is a 4 times 9. So I just want to make myself a note here that 4 times 9 is 36. So I'm going to balance that action out by adding a 36 to the other side, or adding a 4 times 9 to the other side, right? 4 times 9 needs to be added to this side. Okay. Continuing, we're going to work on the square for y. So 2 times m is going to be -2. So our m value is -1. And if we square that, we have 1. So I'm going to be adding 1 to this side. No parentheses or anything that affect this 1. So to balance it off, we're going to add 1 to the other side as well. Okay. When we are factored, we're going to have that 4 coefficient still out front. Inside of our parentheses, this x squared plus 6x plus 9 should factor as x plus 3 squared. Plus 3 is 6, 3 times 3 is 9. The y values, y squared minus 2y plus 1 is going to factor as y minus 1 squared. -1 plus -1 is -2. -1 times -1 is 1, so that checks. And then equals on the other side. Let's clear this. Our -21 plus our 36 plus our 1, so equals 16. Okay. Last step is that these are supposed to be equal to 1. So once I got them equal to something else, like our 16 right here, we'll divide everything by 16. So we'll divide by 16, both sides. And we're going to make sure that that 16 distributes. So we really could just divide each part by 16 if you prefer to write it that way. So in this first one, I'm going to do that next. I've got 4 times x plus 3 squared over 16 plus y minus 1 squared over 16 equals 1. And then we are going to reduce this here as well. Make sure that we're reduced. And I have x plus 3 squared over 4 plus y minus 1 squared over 16 equals 1. I can tell that my major axis is going to be vertical because I have a larger denominator under the y variable. So I have a vertical major axis. Let's list our center. Our center, x and y, the x coordinate is going to be -3. The y coordinate is going to be +1, opposites on both of those. And then I can get my vertices. Since I have a 16 here, square root of 16 is 4. I'm going to need to move 4 up and down in the y direction. So -3 times 1 plus 4, that's 5. And -3, 1 minus 4, which would put me at -3. So I'm going to go up 4, I'm going to go down 4 to get those two vertices. I'm also going to note my minor points. It doesn't ask me to, but in order to graph it, I have to know where they are. So let's just note those as well. They're not called vertices, but they're the directions that we would go along the minor axis. So 2, up and down, or left and right, I should say, past the center. So if we go to the right, we're going to add 2. -3 plus 2 is -1, 1. If I go in the other direction, subtract 2, -3 minus 2 will be at -5, 1. And then I can get the foci. I could have gotten those at any point. I just wanted to get these. They match most closely to vertices. They're not called that, though. So my foci, I better find c. So c squared equals 16 minus 4, a squared minus b squared, which is 12. So c is the square root of 12, which is 2 square roots of 3 up and down. So again, from our center, we will go up and down 2 square root of 3. So our x coordinate stays the same, and we'll have 1 plus 2 square root of 3, and we'll have -3, 1 minus 2 square root of 3. Okay, then draw the graph. All right, the center is at -3, 5. No, -3, 1. I was looking at one of the vertices. -3, 1, that's my center. My vertices are at -3, 5, and -3, -3. My minor points are at -1, 1, and -5, 1. So these are the points that I can use to connect my ellipse to the best of our ability. And then we have our foci, which are just somewhere up in there. You can figure out decimals for those if you want to, but whatever 1 plus 2 square root of 3 is where it's going to land. So if we graph it, just to check out what happened here, I'm going to type in the original function because we always want to make sure we didn't make any mistakes. Plus, let's see, plus a 24x minus a 2y plus a 21 equals 0. There's an ellipse. Its vertices, well, first of all, its center was supposed to be at -3, 1. That looks like it's right in the middle, so I'm going to note that point as my center. I'm just going to call it C, so I don't have too much letters going on my graph here. I have my vertices at -3, 5, and -3, -3. Again, those guys appear in the correct place right here. We got our little minor points here at -1, 1, and -5, 1. Yep, that's where our minor points are. And then our foci, these are the ones I just eyeballed where they should go, but we can put them precisely at, oh, they're even closer, at -3, 1 plus and 1 minus 2 square root of 3. So they're a little closer than I might have drawn them. I just didn't know how far they were away. So that's the location of my foci. All right, and we have another example. I believe it is the last one. Yep. Okay, so this one talks about a medical application of the ellipse is a device called I don't know, I'm not sure what to say for that, so lithometer. One type of this device uses an electromagnetic technology to generate a shock wave to pulverize kidney stones. The wave originates at one focus of the ellipse and is reflected to the kidney stone, which is positioned at the other focus. Interesting. So I'm going to be needing to know something about the focuses I'm suspecting here. Recovery time following the use of this technique is much shorter than with conventional surgery. All right, so here's our example. We've got an elliptical refractor designed so that the distance between the foci is 6 centimeters, and the length of the major axis is 20 centimeters. Okay. The device is calibrated to focus the shock wave precisely on a kidney stone with the other focus. All right, that's what we were talking about up here. Write the equation of the ellipse given the information about the distance between the foci and the length of the major axis. Okay. All right, so like we talked about before, the distance between these major axes, it's a measure of A in either direction, or to the foci, it's a measure of C in either direction, left, right, or up, down. So if I have the distance between the foci, I'm going to have twice the distance I need to go. So my C value is going to be 3, right? So the distance between the two foci, wherever your center is, you're going to add 3 and you're going to subtract 3 to get your 2 different foci. So there'd be a total distance of 6 apart. The same thing for the length of my major axis here. It must be the case that 2A is 20. so that we're going to go 10 in both directions, right? Either left, right, up, down, doesn't matter. Okay. What I need to find is my b value. So c squared equals a squared minus b squared. So I will have c squared, it's going to be 3 squared, equals 10 squared minus b squared. So b squared is 100 minus 9, which is 91. So b is the square root of 91. Okay. Now, for this system, I don't think it matters if we make our ellipse have a vertical axis that's horizontal or vertical, because you're going to be picking this machine up and moving it, I'm sure, to like angle things at this body. So let's just say it's going to be horizontal. We're going to write our equation that has a larger denominator under x. So the a value will go under x. So the equation could be, for part A right here, x squared. I noticed something real quick. I haven't talked about center. Center is arbitrary, again, in this situation, because when you move this machine, the center is just going to pick up and follow along with it. So might as well make the center the origin. So I have made that assumption right here. The center is going to be the origin because on a machine like this, it's going to be moving. Pick its location to be 0, 0 for simplicity. So we're going to do x squared over a squared. So that's over 10 squared, which will be 100. Plus y squared over b squared, square root of 91 squared, which will be 91, equals 1. Okay, so that's how I can represent this equation. I've centered it at the origin here. And I need to find the length of the minor axis. Well, kind of already know that. I know that I go square root of 91 in either direction. So the full length of the minor axis is 2b, or 2 square root of 91. I could approximate that. I'm curious what that is. It's about 2 square root of 91. So it's about 19.08 centimeters. And if a kidney stone is placed at the second focus, what is the distance from the center of the ellipse to the kidney stone? Well, the distance from the center to the kidney stone is c, right? And our c value is 3. So it's going to be 3 centimeters from the center to the stone. So again, this device, 3 centimeters is not very big, so it's probably pressed quite closely to the abdomen, so that you have your center right outside of the body, and then your other thing with the refractor is, again, 3 centimeters further from that. All right. Interesting. All right, so that was our last example.